Hi guys, Dr. Gade is here. In today's class, we're going to solve some numericals in fluid dynamics. But before it, I would like to tell you, for better audio quality, please use your headphone. In solving numericals in fluid dynamics, we often going to use Bernoulli's equation. Let's study Bernoulli's equation. It is P by rho g plus V square upon 2g plus Z is equal to constant, where P by rho g is pressure energy head and V square upon 2g is kinetic energy head and Z is potential energy head. So what is head? It is energy per unit weight. अगर fluid flow हो रहा है तो unit weight of fluid में जो energy होगा, that energy is head. Like potential energy divided by its weight is h, where h is potential energy head and it has a unit of meter. One should note that Bernoulli's equation is valid only for inviscid, incompressible and irrotational flow. What is inviscid flow? Non-viscous flow is inviscid flow. Viscosity must be 0. And what is incompressible flow? Change in density due to flow velocity should not be more than 5%. One should note, if Mach number is less than 0.3, then you can consider it incompressible flow. And what is irrotational flow? Fluid particles are not rotating about their mass centers. Let's do a case study. इस तरह से प्लेट है, फ्लूइड फ्लो हो रहा है और ये बाउंड्री लेयर है एंड वी नो दैट इनसाइड द बाउंड्री लेयर देयर इज अ वेलोसिटी ग्रेडियंट एंड वी आल्सो नो दैट अगर कोई फ्लूइड है तो कुछ ना कुछ तो इसकी विस्कोसिटी होगी ही. नाउ लेट्स टेक आउटसाइड द बाउंड्री लेयर. हियर वी कैन अप्लाई बर्नौलीज इक्वेशन. व्हाई? बिकॉज दो फ्लूइड इज विस्कस yet flow is not viscous, that is we can neglect the viscous effect of fluid in the flow field. Now come to the inside of the boundary layer. We can't apply Bernoulli's equation. Why? Because we can't neglect the viscosity of a fluid in the flow field. You can see there is a velocity gradient. We can't simply assume that velocity profile is linear inside the boundary layer. Also, inside the boundary layer, the flow is highly rotational. So we can't apply Bernoulli's equation inside the boundary layer. But we can apply Bernoulli's equation outside the boundary layer. Now let's solve a numerical. A jet of water issues from a nozzle with a velocity of 20 meters per second and it impinges normally on a flat plate moving away from it at 10 meters per second. The cross-sectional area of a jet is 0.01 meters square. The density of water is 1000 kg per meter cube. The net force developed on the plate is, इस तरह का सिचुएशन दिया गया है. We have to find the net force developed on the plate. From Newton's second law of motion, summation of force in x direction is rate of change of momentum in x direction, which is this, where m dot is mass flow rate, which is equal to the density into discharge, and discharge is area into v, where v is velocity of striking, which is equal to the v minus u. So summation of force in x direction is rho a into v minus u into final velocity vector minus initial velocity vector, where final velocity vector in x direction is nothing but the u. So after putting the values, we will get summation of force in x direction is minus 1000 Newton. So far we were considering water as a system and we were solving for that. So minus 1000 Newton is force on water by plate. It is negative because force on water is in negative x direction. So force developed by water on plate is negative of that one, which is 1000 Newton. So option A is correct. One should note that in mass flow rate, if you take it velocity of a jet, then you will get option D, which would be wrong. Let me tell you one more thing. Later in fluid machinery, you will study that in case of a Pelton wheel turbine, it is equal to the velocity of a jet, not V minus U, because it is the case of theoretically infinite number of plates. पेल्टन व्हील टरबाइन में एनी टाइम कोई ना कोई प्लेट रहता है. दैट्स व्हाई इफेक्टिवनेस ऑफ स्ट्राइकिंग इज 100%. सो वी डायरेक्टली टेक वेलोसिटी ऑफ जेट. नाउ लेट्स सॉल्व वन मोर न्यूमेरिकल. Water flows through vertical contraction from a pipe of diameter d to another of diameter d by 2. The flow velocity at the inlet to the contraction is 2 meters per second and pressure is 200 kN per meter square. If the height of the contraction measures 2 meters, then pressure at the exit of contraction will be nearly, इस तरह का situation दिया गया है. We have to find P2. Simply applying Bernoulli's equation, Here Z1 will be 0 because we are taking it as reference. After further solving it, we will get this. Now we have to find value of V2. So from continued equation, V2 is 4 times V1, which is coming out 8 meter per second. Now putting this value and further solving it, we will get P2 is approximately 150 kilonewton per meter square. So option C is correct. Let's solve one more numerical. A water container is kept on a weighing balance. Water from tap is falling vertically into the container with a volume flow rate of Q. The velocity of water when it hits the water surface is U. At a particular instant of time, the total mass of container and water is M. The force resisted by the weighing balance at this instant is, इस तरह का सिचुएशन दिया गया है. At any particular instant, total mass of water plus container is M. So weight of the water plus container is mg. Let's take this as equation 1. Falling water from tap will also exert force into the weighing balance. So from Newton's second law of motion, summation of force in y direction is m dot into final velocity vector minus initial velocity vector. Final velocity vector at this instant is u, and we are taking initial velocity vector 0. Why? Because nothing is given. अगर दिया भी रहता तो it will be negligible as compared to u. So solving this equation, we will get summation of force in y direction is rho qu. This one is the force on vertically falling water in positive y direction. So force into the weighing balance is opposite of rho qu. Here negative sign indicates it is in downward direction. So net reading in weighing balance is mg plus rho qu. So option A is the correct answer. Let's solve another numerical. A venturimeter of 20 mm throat diameter is used to measure the velocity of water in a horizontal pipe of 40 mm diameter. If the pressure difference between the pipe and throat section is found to be 30 kilopascal, then neglecting the frictional losses, the flow velocity is something like this is given. We have to find V1. Simply applying Bernoulli's equation, Z1 and Z2 will get cancelled out because pipe is at horizontal level. On further solving it, we will get this. Now we have to find the value of V2. From continuity equation, we get V2 is equal to 4 times V1. On putting this value further, we will get V1 is equal to 2 meter per second. So option D is correct. Let's solve another numerical. Figure shows the schematic for the measurement of velocity of air, which density is 1.2 kg per meter cube, through a constant area duct using a pitot tube and a water tube manometer. The differential head of water, whose density is 1000 kg per meter cube, in 2 columns of manometer is 10 mm. Take acceleration due to gravity as 9.8 meter per second square. The velocity of air is. Before solving this numerical, I would like to teach you something. Let's assume इस तरह का एक पाइप है. Water at this portion will rise because of pressure energy of the flow. So H1 is pressure energy head. If I add this type of arrangement into it, then water will again rise, but now water level will rise because of the combined effect of pressure energy and kinetic energy. So H2 is pressure energy head plus kinetic energy head. So if H2 minus H1 is H, then flow velocity will be under root 2gh, where h is the height of liquid column whose velocity we want to measure. Now come to the question. This type of arrangement is given and we have to find flow velocity. By using above formula, V is under root 2gh. If you think h is 10 mm, then my dear, you are absolutely wrong. Why? Because 10 mm is the height of water column and we want to find the velocity of flow of air. So h must be of air column. By applying simple manometric equation, one can easily get this, where h is the height of air column, x is the difference in level of manometric fluid in manometer. This one is the density of manometric fluid. This one is the density of a fluid whose velocity we want to measure. Now by putting values we will get h is equal to approximately 8.3 meter. So velocity of flow will comes out approximately 12.7 meter per second. So option C is correct. Let's solve one more numerical. Water is coming out from a tap and falls vertically downwards. At the tap opening, the stream diameter is 20 mm with uniform velocity of 2 meter per second. Acceleration due to gravity is 9.81 meter per second square. Assuming steady, inviscid flow, constant atmospheric pressure everywhere, and neglecting the curvature and surface tension effect, the diameter in millimeter of the stream, 0.5 mm below the tap, is approximately something like this is given, and we have to find d2. Applying Bernoulli's equation, since everywhere pressure is atmospheric, so these two will get cancelled out and z2 will be 0 because we are taking it reference. On further solving it, we will get v2 is approximately 3.7 meter per second. From continued equation, we will get d2 is approximately 14.7 millimeter. So option B is correct. Let's solve our last numerical. A tank open at the top with water level of 1 meter as shown in the figure has a hole at a height of 0.5 meter. A free jet leaves horizontally from the smooth hole. The distance x in meter where the jet strikes the floor is something like this is given, and we have to find the value of x. One should note that in this flow, velocity of particle will be something like this. That is, in x direction, velocity is constant, and in y direction, velocity is increasing with uniform acceleration of g. Let me tell you one more thing. Suppose we have a stone at a certain height and we drop this stone at time is equal to 0, and this stone reaches to the ground at time is equal to t1. And we have another situation where at time is equal to 0 we are throwing a stone from the same height like this, and it is taking time t2 to reach the ground. It is interesting to know that t1 will be equal to t2, that is, time taken by both these stones to reach the ground will be same, because in y direction acceleration is constant for both. So from Newton's second law of uniform accelerated motion, we can write this, where s here is 0.5 meter, u here is 0 because initially in downward direction velocity is 0, and a here is small g. After solving this equation, we will get t is equal to 1 upon under root g second. That is, time required to reach the ground by z particles is 1 upon under root g second. And velocity is equal to displacement upon time. So displacement is equal to velocity into time. On solving this equation, we will get x is equal to 1 meter. So option B is correct. That's it for today's class. Thank you for watching this video. If you liked it, please subscribe my channel and do share it with your friends.